Welcome to the Journey Chez Chem. Please do the 2 warm-up questions to the best of your ability, and we will review them in a moment. In addition to answering number 1, let's do a little bit of review of the ideal gas law. Well, originally we have the ideal gas law, and we know that moles is equal to grams over molecular weight. And you'll recall that molecular weight is the gram formula mass, or the atomic mass units for the compound that is taken off of the periodic chart. And I'm going to substitute my grams over molecular weight for my moles. And therefore, PV equals GRT over molecular weight. And there are different textbooks that use different letters for these two. However, I like the G and the MW because it's clear what we're talking about here. And sometimes you might see a lowercase m here and an uppercase M here, and there's so many different M's, I just get so confused. And therefore, I want to see them nice and straightforward. Now, I'm going to rearrange this again for molecular weight. And again, this is a little bit of review before we go into solving the problem. Well, molecular weight, therefore, is equal to, I bring it up, I multiply it under the division, and therefore it equals GRT. And then to isolate and remove the PV, which is multiplied, I undo it by dividing. Now, when I have it in this state, I can solve it for density. And density is equal to mass over volume. So it's already in that form, and now I will just remove the things that are in the way there. And therefore, my molecular weight times the pressure divided by RT is equal to grams over volume, and that would be the density. Now, there is a number in the warm-up question of volume, and with this equation, I don't need to use that. However, some students may have chosen, because we know that the element is neon, that you could solve for the mass and then change the mass, and then divide the mass by that volume, and you would also get the density. However, I prefer to just go ahead and solve it for density. Either way is acceptable. Now, I know the molecular weight for neon is 20.2 grams per mole, and it's important to follow through with my units, 20.2 grams per mole. And the pressure that I'm given in the problem is 760 torr. And because I'm given torr, I want to use my ideal gas constant in torr. And that would be 62.4 torr liters per mole Kelvin. And then I multiply that by the temperature. And the temperature is 25 degrees Celsius. And therefore, I take 25 degrees Celsius plus 273, and I get 298 Kelvin. It's a matter of substituting the values in correctly. And when I do the math, I get 0.8255. I look back to my original problem, and I want 2 significant digits in my final answer. And therefore, this 5 rounds the 2 up, and my final answer is 0.83. And my unit is grams per liter. And that's both a little bit of review and working out a density problem. And I'll be right back. Number 2 is a volume problem. And first I must have the balanced equation. And then I write down what am I given and what am I looking for so that it keeps me going in the right direction. Now notice that this volume here is in centimeters cubed, and my standard molar volume is in either decimeters cubed or liters. And therefore I must change this number to decimeters cubed before I can change it to moles. And there are 45.5 centimeters cubed of oxygen that I am beginning with. Ooh, I get to draw a long line, You know how much I love those lines. So then I'm going to change it to decimeters cubed. I'm going to decimeters cubed and I'm canceling centimeters cubed. And I know that we have to practice and practice these conversion factors, so let's do it again. We have 10 centimeters is equal to 1 decimeter. Therefore, if I cube 10, I get 1,000. There are 1,000 centimeters cubed in every 1 decimeter cubed. And then I'm going to change it to moles. And 1 mole of any gas, and in this case we're talking oxygen, is 22.4 decimeters cubed of that gas. And then I change my moles to a different compound using the mole ratio in the balanced equation. And I'm looking for the moles of water, and I want to cancel my moles of oxygen. And then I change my volume from moles back to volume. And 1 mole of any gas, in this case we're talking about water, is 22.4 decimeters cubed of water. And I could have just as easily said liters, that would be fine. When I do the math, I get 0.091 decimeters cubed. I look back to my original problem and I want 3 significant digits. Therefore, it would be 0.0910, or I could put it in scientific notation of 9.10 times 10 to the minus 2 decimeters cubed of water. And that's a volume-volume type of problem. Now, the beauty of this problem is I'm going to use this problem to show you how we would figure this out at non-standard conditions. Because as you recall, 22.4 liters is only 1 mole under standard conditions, and that's why we call it standard molar volume. Well, I'm just going to pick some numbers out of the air, and let's see, what would it be if it was actually at 65 degrees Celsius and 710 torr? What would the volume be? And the way that we do this is very similar in that we change our volume to moles. So this process would be the same up to this point. And then I would want to go to my moles of my oxygen. There are 2 different types of problems that you'll see with this, and this would be from a volume. So we change our volume to decimeters cubed and then standard molar volume and then the mole ratio, and we find out how many moles of the water that we have. And if we were doing this, we would find that we have 0.004062 moles of water. And then we would take those moles and put them into the ideal gas law. And we would solve it for volume. PV equals nRT, and therefore volume equals nRT over the pressure. And then we just substitute those values into the ideal gas law. And we have 0.004062 moles of our water. And because I'm using a torr as my non-standard condition, I'm going to use my torr ideal gas constant. Torr liters per mole Kelvin. And then I need the temperature. And we said the temperature was 65 degrees Celsius plus 273 gives me 338 Kelvin. And then I divide it by the pressure of 710 torr. That's not so bad. And when we solve it mathematically, then we would find that our volume is equal to 0.1206, and we want 2 significant digits, and therefore my volume is 0.12 liters or decimeters cubed of water. And that's how we would do that if we were starting with a volume. We would then get, the important part here is to go to the mole ratio so we can change from one compound to the other. This is critical. And then we would put the numbers into the ideal gas law. And now I want to review with you the problem that you have on the worksheet, the sample the example problem, and we'll talk about that in a moment. The second type of problem that we have where we are going to non-standard conditions would be if we were originally given grams. And this is very much like the example that you have on worksheet G. And we get a balanced equation first, and I write down what am I given and what am I looking for. Then I change my grams to moles, and we've done this many times. And then we go to the mole ratio to change to our new compound. And we're looking for oxygen. And I love this ratio of 3 to 2. It's just great. And we get our moles of oxygen. And then I have my ideal gas law. And I rearrange it for volume is what I'm looking for. And then I substitute in the values. And when I have my degrees Celsius, I must change it to Kelvin. I must use the R constant for atmospheres because the unit that I'm given my atmospheres in is in ATM. I'm given pressure in ATM, I should say. And then I do the math. And remember, we always put equals in between. 0.1284 times 0.0821 equals times 298 equals divided by 3.5 equals 0.8975 because we go 4 significant places past the decimal, and then we round to 3 significant digits based on the numbers given in the example problem. And that's how you do those problems. And you have 3 to do this evening, and you should not have a problem. You have the example on there, and we've talked about the example, and we can go from volume or we can go from grams. Well, that was some fun, and this is the last topic that we have to discuss before the assessment comes up. And you know that you're going to have a quiz on Wednesday, and there will be 5 problems, and they're all different types of problems. There'll be some volume, some mass volume, some ideal gas law. It's just a mixture, but there's only 5, so you could possibly guess which ones you may see. And then we'll have review, and then we'll have an assessment the following week. Well, I can't wait to see you tomorrow. Bye.